Think about the cold for a second. How cold can it get? You know there's a theoretical maximum temperature for heat, but when it comes to the cold, intuition tells you, the more you cool things down, the closer you get to the limit. And this limit has a name. Absolute zero. 0 Kelvin. Minus 273 degrees Celsius. The point where everything stops. Wrong. It's not a technical problem. It's not that we need better equipment. Absolute zero is physically impossible to reach, and not just for one reason. For two. Two completely independent reasons from different branches of physics, both pointing to the same conclusion. Nature forbids it. The first reason comes from thermodynamics. It's a law as fundamental as gravity, and it dictates that no matter how good your equipment is, you're never going to get there. The second reason is much stranger. It doesn't come from heat, it doesn't come from energy, and it doesn't come from any technological limitation. It comes from the fundamental structure of reality itself. And once you understand why particles simply cannot stop, you'll realize the mistake was never about temperature. It was about what the universe actually allows to exist. First, forget what you think you know about temperature. It isn't what you feel when you touch a hot surface. It isn't the number that pops up on the street thermometer. That's just our perception of temperature. And perception is a treacherous thing when you're trying to understand physics. Temperature is movement. More specifically, temperature is the average kinetic energy of the particles in a substance. When an object is hot, its molecules are moving fast, vibrating, colliding, and spinning at absurd speeds. When it's cold, they slow down. The colder it gets, the slower they move. And the idea behind absolute zero is simple. If temperature is movement, zero temperature means zero movement. The particles stop completely. It was from this logic that scientists built the Kelvin scale. In the 19th century, the British physicist William Thomson, who would later become Lord Kelvin, realized that if you extrapolated the behavior of gases at low temperatures, you would reach a point where volume and pressure would hit zero. A mathematical floor. The absolute coldest anything could possibly be. He named this limit absolute zero, which is equivalent to minus 273.15 degrees Celsius, minus 459.67 Fahrenheit, 0 Kelvin. The classical logic is flawless. If temperature is kinetic movement, and if you remove all the kinetic energy from a system, the particles stop. And if the particles stop, you've reached absolute zero. It's linear, it's elegant, it's Newtonian. Here's another implication of this definition that's worth pausing to understand. The Kelvin scale isn't like Celsius or Fahrenheit, where zero is just an arbitrary reference point. 0 Celsius is where water freezes. 0 Fahrenheit was defined by the melting point of a mixture of salt and ice. Those zeros have no fundamental physical meaning. You can easily have negative temperatures in Celsius. 0 Kelvin is different. It is absolute zero in the strictest mathematical sense. It's the point where the kinetic energy of particles reaches its theoretical minimum. There are no negative temperatures in Kelvin in the classical sense, because there is no such thing as less than zero movement. The scale starts at the floor and only goes up. This conceptual elegance led 19th century physics to assume that the floor was actually reachable, that with good enough equipment, all you had to do was cool, and keep cooling. 2 centuries of intuition pointing in the exact same direction. And that is exactly where the mistake begins. Physics has a problem for you. Removing all kinetic energy from a system isn't just hard, it's impossible. There's a law that guarantees it. A German chemist named Walter Nernst formulated it between 1906 and 1912. He's not as famous as Einstein or Bohr, but what he discovered is one of the most unforgiving laws in all of physics. It became known as the third law of thermodynamics, and essentially, it states the following. The closer you get to absolute zero, the harder it becomes to remove heat from a system. Not proportionally harder, exponentially harder, asymptotically harder. To understand why this happens, you need to understand the concept of entropy. Entropy is a measure of disorder, of the number of possible states a system can take on. When a system is hot, the particles have plenty of room to move around, many possible energies, and countless configurations. High entropy. As you cool it down, you start restricting those possibilities. The particles slow down, taking up more orderly configurations. the entropy drops. Here's the problem. To remove heat from a system, you have to transfer that energy to the environment. And the efficiency of this transfer depends on the temperature difference between the system and the reservoir absorbing the heat. The colder the system gets, the smaller this temperature difference becomes, and the smaller the difference, the less efficient the transfer. Here's the brutal part. Going from 10 Kelvin to 1 Kelvin takes way more energy than your previous drop. The system's already frozen, and every step costs exponentially more. The effort to squeeze out that last bit of heat, it approaches infinity. You can't finish the job. Each step burns more fuel just to make less progress. This has a name. It's an asymptotic approach. And do you know a very famous historical analogy for this? Zeno's paradox. Zeno of Elea, a Greek philosopher from the 5th century before Christ, argued that to travel any distance, you first need to travel half of it, then half of what's left, then half of that, and so on infinite steps before reaching the destination. The absurd conclusion was that movement is impossible. Obviously, we're here, and movement exists, so the paradox has a mathematical resolution. But the structure of the argument is the exact same one that appears on the path to absolute zero. Every cooling technique physicists built hits the same wall. Laser cooling uses photons to steal momentum from atoms. It works great, but has a limit. Evaporative cooling kicks out the hot atoms, leaving the cold ones behind, like blowing steam off your coffee. Also has a ceiling. Adiabatic demagnetization squeezes energy from particle spins, pushing further than any other method. But they all crash into it. Asymptotic, infinitely close, never actually there. This became evident in practice long before Nernst formalized the law. In the late 19th and early 20th centuries, physicists entered a race to liquefy the most stubborn gases: oxygen, nitrogen, hydrogen. Each breakthrough brought them closer to absolute zero. In 1908, the Dutch physicist Heike Kamerlingh-Onnes finally liquefied helium, reaching temperatures of just over 1 Kelvin, and received the Nobel Prize in 1913 for it. It was an extraordinary record. It was also just the beginning of the asymptote. With every new lab, every new technique, progress slowed down. The curve flattened out. Absolute zero kept receding just a little bit further. This is the thermodynamic verdict. Nernst's third law states that you can never reach absolute zero in a finite number of steps. It's not a limitation of our engines, but an unbreakable rule of nature. That was the first verdict. But remember when I said the second one would shatter your intuition? The second one doesn't come from heat. It doesn't come from entropy. It doesn't come from anything thermodynamics touches. Even if you somehow broke the third law, even if you had infinite power and infinite steps, there would be a completely different reason why absolute zero would still be impossible. And it comes from the very fabric of reality itself. In 1927, a 25-year-old German physicist named Werner Heisenberg published something that flipped our understanding of the universe upside down. Not a theory about planets or atoms, a statement about what we can actually know about any particle. Heisenberg's uncertainty principle says this: you cannot know, at the same time and with perfect precision, both the position and the momentum of a particle. Mathematically, this is expressed as dx multiplied by dp is greater than or equal to divided by 2, where dx is the uncertainty in position, vp is the uncertainty in momentum, and is the reduced Planck constant. The more precisely you know the position of a particle, the less you can know about its momentum. And the more precisely you know the momentum, the less you can know about the position. It's not a matter of having bad instruments. It's not a matter of disturbing the particle during measurement. It is a fundamental property of nature. The particle itself simply does not possess definite values for these two quantities at the same time. Now apply this to absolute zero. At absolute zero, what would happen to a particle? It would be completely at rest. Zero momentum. Exactly zero. And it would be somewhere in space in some definite position, inside a crystal, inside an atom. This directly violates the uncertainty principle. If the momentum of a particle were exactly zero, the uncertainty in momentum would be zero. dp equals zero. But Heisenberg's equation says that dx times dp must be greater than or equal to j2a non-zero number. If dp is zero, then dx would have to be infinite. The particle could be anywhere in the universe simultaneously. Think about what that means. A particle at complete rest would have no location anywhere. It could be anywhere in the universe. But particles, the stuff of matter, have to have positions. They can't be entirely still. So you have a paradox. For a particle to have exactly zero momentum, it would need to have a completely undefined position. And to have a definite position in some finite space, it must have some uncertainty in its momentum, which means it cannot have exactly zero momentum. So particles with a real position have to keep moving. Not because something's pushing them. Not because heat's still lingering. But because quantum math demands it. Absolute zero means all particles have zero momentum and exact positions. The uncertainty principle forbids both at once. Absolute zero breaks quantum mechanics. This isn't just a measurement problem or a science gap. It's the universe saying what can exist. Particles can't hit zero momentum. The universe won't let them. There's built-in, irreducible movement that no cooling technique can kill, because it's not from heat. It's hardwired into quantum reality. This is where most people get it wrong. They think the uncertainty principle is about clumsy measurement. You shine light on a particle, the light hits it, momentum changes. The measurement messes it up. That's the usual picture. Heisenberg went much deeper. He said there's no hidden reality where the particle has both properties. The problem isn't the measurement. These properties don't coexist, period. Not before, not during, not after you look. Einstein didn't buy it. In 1935, he created the EPR thought experiment with Podolsky and Rosen. Trying to prove quantum mechanics was incomplete, that there's hidden reality where properties exist, but we don't know them. Decades of Bell test experiments proved him wrong. There's no hidden reality. The uncertainty is real. So quantum mechanics doesn't just make absolute zero hard. It forbids it. It's not an engineering problem. It's a logical contradiction. But this raises an obvious question. If particles can never come to a complete stop, what is the absolute minimum energy they can have? The answer lies in the concept of zero-point energy. And this is where quantum physics stops being abstract and becomes something you can actually measure. Every quantum system has a ground state, the lowest energy it can reach. Classical thinking says lowest energy is zero. A particle at rest, zero kinetic energy. Wrong. For a quantum oscillator atoms in a crystal lattice, the ground state energy is 1020. That's not zero. Can't reduce it. Can't extract it. This is the absolute minimum energy a particle can have, and it's non-zero. This is zero-point energy. The quantum floor. The residual energy left over even when you've removed all possible heat. But it's not just a mathematical prediction. There is direct physical evidence that this energy exists and is real. Liquid helium is the first proof. Everything solidifies when cold enough except helium. At normal pressure, helium stays liquid even at the coldest lab temperatures. Why? Zero-point energy in helium atoms is too strong to let them lock into solid form. The atoms keep vibrating, not from heat, but from quantum vibration built in, and that's enough to stay liquid. To freeze helium, you need pressure. Force the atoms together. Without pressure, absolute zero can't freeze it. The quantum floor keeps it flowing. The Casimir effect is the second proof. In 1948, physicist Hendrik Casimir predicted two uncharged metal plates placed nanometers apart would attract each other. Not electrical, not gravity, not heat, but quantum vacuum fluctuations. Empty space isn't empty. Quantum mechanics says even in a vacuum zero particles, there's constant energy flickering, fields oscillating at zero-point energy. Between two plates, some frequencies can't fit, they're too big for the gap. Outside, all frequencies exist. That creates a pressure imbalance, more energy outside, and the plates get pushed together. In 1997, American physicist Stephen Lemoreau measured the Casimir effect precisely for the first time. To give you an idea of the scale, at a distance of 1 micron, the attraction generated between the two plates is equivalent to the weight of a few bacteria, a minuscule force, but perfectly measurable by high-precision equipment. It was there. Exactly the way quantum mechanics predicted. The vacuum-pushing plates that had no reason to move. This attraction proved in practice what the calculations had predicted. The quantum vacuum is seething with energy. And this energy, the fundamental bedrock of the universe, is palpable, measurable, and impossible to extract. We know the floor exists. We know it's real. The question now is, how close have we gotten to it? Just how close have modern labs pushed toward absolute zero? The hunt for absolute zero is a story of human persistence hitting nature's limits and finding things nobody expected. Getting to micro and nanokelvin temperatures meant inventing totally new cooling. Laser cooling came in the 1980s. Chu, Koen Tanuji, and Philips built it, and won the 1997 Nobel. The trick: use photon momentum to break atoms. Tune the laser just below the atom's frequency, so only atoms moving toward the beam absorb photons and slow down. It's like a light breeze that stops atoms from moving in every direction at once. Combined with evaporative cooling, where the hottest atoms escape from a magnetic trap, leaving the colder ones behind, these methods paved the way for the nanokelvin regime. Using combinations of these techniques, laser cooling, evaporative cooling, adiabatic demagnetization, and refining each of them over decades, modern laboratories have reached unimaginable temperatures. In 2003, physicist Wolfgang Ketterle's group at MIT cooled a sodium gas to about 500 picokelvins, 500 trillionths of a Kelvin. Written as a number, that's 5 times 10 to the negative 10 Kelvin, a minuscule fraction of a billionth of a degree above absolute zero. In 2021, experiments on the International Space Station, using even more refined techniques, briefly reached temperatures of approximately 100 picokelvins in ultra-cold gas samples, 100 trillionths of a Kelvin. Still, the advancement remains asymptotic. Every new decimal place of progress requires exponentially more effort than the last. The curve on the graph approaches endlessly, but it never touches the zero axis. But here's what no one expected. The pursuit of the impossible produced something completely new. In 1924 and 1925, Bose and Einstein made a wild prediction. At ultra-low temperatures, bosons could drop their individual identity and collapse into one quantum state. They'd stop being separate particles and become one giant quantum thing, a condensate. The prediction sat for 70 years. Not a theory problem, a technology problem. You couldn't get cold enough to test it. Making a condensate needs the quantum waves of atoms to expand until they overlap. Billionths of a Kelvin. That technical barrier took decades to crack. June 1995, Cornell and Wieman succeeded. Rubidium atoms cooled to 170 nanokelvins, 170 billionths of a Kelvin, made the first Bose-Einstein condensate ever. Months later, Ketterle made another with sodium, going deeper. All three won the 2001 Nobel. The Bose-Einstein condensate is wild. At room temperature, atom waves are tiny and invisible, they act classical. But cool them ultra-low. Waves expand, and below a threshold, they overlap into one giant wave. The atoms lose their identity. You can't point to one atom in the condensate. They're all in the same quantum state. The first photo of a condensate showed exactly what theory said. A velocity spike at 0 atoms collapsed into one quantum state, acting like a single wave. You can photograph it, measure it, watch it flow through the container with 0 friction. It's a state of matter that doesn't exist anywhere in your daily life. Superfluidity and superconductivity emerge near absolute zero too. Liquid helium below 2.17 Kelvin becomes superfluid, flows through microscopic cracks with no resistance, climbs walls, defies gravity. Superconductors kill all electrical resistance and shove out magnetic fields. Magnetic levitation. All of it. All this exotic physics came from chasing the impossible. The asymptote isn't a dead end. It's a discovery machine. The closer we get to absolute zero, the more the universe reveals behaviors that exist nowhere else. But all of this brings us back to the bigger question. What does the fact that absolute zero is impossible tell us about the universe? It starts with a mistake, but not just any mistake. Using the wrong physics to think about the problem. Newtonian physics, what they teach in school, is dead accurate at our scales. How rocks fall, planets orbit, engines work. It works because quantum effects are invisible at human scales, so tiny you ignore them without losing precision. But extreme cold changes the game. Individual particles matter. Quantum mechanics can't be ignored. The rules flip. It's like using a street map inside a cell. The map works at its scale: roads, cities, human distances. But at nanometer scales, the roads don't exist. You didn't get a bad map. You got the wrong map for the wrong scale. Classical physics is that map. Perfect in its domain. Useless outside it. Newtonian thinking. Temperature is motion. Kill the motion. Temperature hits zero. Works fine normally. Push it to extremes and it cracks. Not because intuition failed, but because something deeper emerges. Heisenberg and Nernst together reveal something profound about the cosmos. The universe has background noise you can't kill. Baseline energy. A fundamental vibration that's not an imperfection or residual heat. It's built in. Absolute zero is impossible because a particle would need a fixed position and zero momentum at once. Quantum mechanics says that's not hard to measure. It's a contradiction. The question sounds okay, but it mixes things that don't mix. It's logically impossible, not a tech problem. The quantum floor zero-point energy, vacuum fluctuations, reality's built-in hum isn't a flaw. It's a feature. It's why helium stays liquid, why the Casimir effect works, why condensates exist. It's why matter has structure instead of collapsing. Without zero-point energy, electrons crash into nuclei. Matter can't exist. Absolute zero being impossible isn't a cosmic design flaw. It's what holds everything together. Your intuition was wrong, but not stupid. Classical physics nailed it at human scales. It's only at extremes that it breaks. And what appears instead are the cosmos's deepest mechanics. A universe that won't stop, that hides energy in its vacuum, whose laws go beyond simple thermodynamics. Think about what happened. Scientists hunted absolute zero, hit a thermodynamic law saying never, kept going, found a quantum law saying even if you did, it breaks the system, kept going anyway. And chasing the impossible, they discovered new states of matter, measured vacuum energy, built MRI scanners, atomic clocks, gravitational wave detectors. We learned the universe has a floor, a minimum level where matter and energy stop. This isn't a defeat for science. It's one of our deepest discoveries. The universe has a floor, and the closer we get to it, the more it shows us how everything works. You know more about temperature limits than most physics students now. Like this if it shattered your intuition. Subscribe if you want to keep digging into fundamental physics. There's way more coming.